Good morning, everyone, Mr. Chairman, gentlemen, ladies and gentlemen, dear colleagues. I am really happy to have the opportunity to present this keynote lecture related to the use of high-strength steel in seismic resisting buildings. So, in I would say quite, let's say, complicated flowchart, you can see what are the actual situation of the seismic design procedures and what are the main strategies to apply. Speaking about the strategies, which you can see in the right side of the slide, you can see there are three: reducing seismic forces, enhancing damping, and adjusting structural properties. The application of high performance materials among is also high strength steels. The last one, adjusting structural properties, is the strategy to be applied. I want to summarize the content of this presentation. After a short introduction, we will speak about the cyclic response of European structural steels. After, we will discuss a little about the weld details and G-stab in the situation when we have two different steel grades to be connected. We will speak after about dual steel buildings frame and dual structures with fused components and recentering capacities in the idea of application of fused components. And at the end, summarizing, concluding remarks. Speaking now about what does mean structural robustness of structure which are prone to moderate and let's say maybe high risk earthquake. We have to say that the usual procedure in seismic design is to use so-called dissipative structures. Dissipative structures, it means we will have in the structure configuration ductile members which are able to develop plastic deformation, and through this plastic deformation to dissipate the kinematic energy induced by the earthquake. And also we need to have overstrength components, which in principle they are sized to remain elastically during the earthquake, which practically will maintain standing up the structure. A performance-based design philosophy can apply in order to have some criteria for a progressive development of damages during the earthquake. Okay. The use of high-strength steel in buildings is not so old, and the use of high-strength steel in seismic resistant buildings is even later applied after the use in common building structures. Initially, at the end of, let's say, 20s, started to apply high-strength steel, not exactly in order to come with some advantages for seismic design, but in order to obtain some, let's say, economy due to the fact using high-strength steel in members which are designed by resistance criteria, the cost of material is lower due to the fact the weight of these members will be reduced if comparing with conventional steel. Some examples. One of them is Mafre Tower in Barcelona, which was realized in 91, 92, which the effect of application of 460 steel grade reduced the weight of the columns with 24%. Other examples is the Colgate Center in Jersey City, which was finalized at the end of 2010. A really big construction. Had the same effect applying the 460 grade in the place of 355, for instance. In this case, the saving, again, by replacing the steel in the columns, was lower with 17%. And we can continue with examples like Yokohama Landmark Tower in 1993, and the last example, because there are also others, Freedom Tower, which was finished in 2015, in which again the columns up to the height of 76 meters was realized by 450, 460 steel grade. The presentation I am going to do today is based on a series of large research projects, most of them funded by European Union, but also, for instance, the first one, which was supported by Romanian government. You have to know, Romania is a seismic country. In fact, all the territory of Romania is a seismic territory, of course, with different zones, with different seismic risk. I will speak about this during the presentation. On the other hand, I want to tell you that some years ago, in 2017, the High Performance Steel Structure Research Council was founded. It was founded by the University of Delft and the Tsinghua University in China, and of course with much more other partners. And they started to organize the first one in 2018, a series of workshops dedicated to the use of high performance steel in building construction. Of course, high performance is referring particularly to high strength steels. The last one, it was last year in November the last workshop organized by this council. It was in, as I told, in somewhere 12, 13 November last year. It's first subject in the presentation refer to the low cycle behavior of European steels. You have to know, as I told you, in principle, in ductile components of seismic resistant structures, usually we are applying mild carbon steel to get enough capacity to develop plastic deformation. But there also are those overstrength components which usually are designed to remain elastic during the earthquake, and in which is and it would be the right place to apply high strength steels in these seismic resistant structures. However, sometimes the real earthquakes are overpassing the design earthquake which has been used to size the members and their sections. So in such a case, even those overstrength members, which could be realized by high strength steels, must be able to develop some plastic deformation. And having this in mind, the interest to investigate the capacity, the performance in low cycle fatigue of high strength steels has been, let's say, conducted to have a systematic research. In the equal joint project, which was one of those I presented before, a project funded by the European Union, dedicated mainly to beam to column connections in dissipative seismic resistant structures. One of the chapters has been devoted to this problem of investigating the low cycle fatigue performance of European steels. We have investigated 4 steel grades: 275, 355, 460, and 690. The last 2 are the high strength steels. You have here here the tensile test. Now in this slide you can see the you have here the tensile test, and if you look to the stress strain curves, you can see that practically we have a really good ductility for 460 steel grade, and not at all bad for 690. Even it is lower compared with the conventional steel results. Related now about the low cyclic fatigue of the same, let's say, steel grades, we have done 3 different types of tests. We have used constant amplitude loading protocols with 4 different amplitudes of strain. We have used a variable amplitude protocol with increasing strain, and we have also investigated the so-called near fault loading protocol, where practically let's say an irregular variation of the strain has been considered. We can look now a little about the failure modes of the specimen which have been tested for low cyclic fatigue. The problem of low cyclic fatigue using, let's say, harmonic loading is difficult due to the fact in compression part, in compression, let's say, loading, they are very sensitive to buckling. That's why there are only a few reports in the literature where such a kind of results have been presented. We can observe here there are 4 different types of failure we can obtain in such a kind of low cyclic fatigue test. So we have fracture making, we could have non-sway buckling, we can have so-called sway buckling. This is the problem, the buckling, and we have this bulging failure. Looking now to the results, there is the results for constant amplitude loading. What is really surprising is to observe that both 2 high-strength steels, 460 and 690, have shown a really very good behavior. I would say comparable with the one of conventional mild carbon steel. And even more, even the variable amplitude test show similar results. If we want to try at this moment some concluding remarks based on this test, of course, much more, let's say, tests have been done than the one I have selected for this presentation. There are 2 main, let's say, aspects to be emphasized. Although the tensile strength of field ratio of high strength steel is smaller compared with the lower grade steel, mild carbon steel, the ductility of high strength steel is much more higher than the figures we are let's say found in the nominal strain requirements in let's say the codes. Practically they are leading to similar number of reversals to failure for all the tested steel grades. The second one, we have observed that for variable strain amplitude, all mild carbon steel present cyclic hardening, while high strength steel exhibits both cyclic hardening but also some small softening. This is also supporting the ductility capacity of this steel. Of course, we are speaking about low cycle, let's say, test with so-called, let's say, very small, let's say, cyclic speed. So we have to go now to the dual steel connections. We are speaking practically about the well detail between two steel grades. In the beam to column structures, when we are intending to apply high strength steels, for instance, in columns which are non-dissipative, and mild carbon steel in the beams which are dissipative, we are obliged to connect each other and to weld each other. So we found that it is interesting to study the weld details on the T-stub specimens. You can see here the T-stubs, and you can observe the steel grades which have been considered. The T-stubs have been unstiffened and stiffened, and they are practically welded, so with bevel welding. A large number of specimens have been tested for this, to see if there are some problems due to the welding of two different steel grades each other. These are the tensile results for, let's say, the materials used to realize the specimens. You can see practically the nominal values are close to the actual steel, so no big difference in between. Here in the table you have all the types with different steel grades which have been tested. As you know, in what concerns the failure modes of T-stubs, the T-stubs which are bolted in the structure, we have two modes. The first one, which is ductile, the second one, which is semi-ductile, and the third one, which is fragile. The problem with ductile mode, which is very good in terms of ductility, is that they are very deformable, and also always we can have only let's say partial strength connection, which are not accepted in moderate and high high risk seismic prone structures. The fragile mode is good because you can obtain always full strength steel, full strength connections. But anyway, this fragile failure in case of let's say extreme earthquake could be dangerous to accept. That's why the attention was mainly focused on two mode, on the two failure mode, the one which is semi-ductile. So, and you can see here by design the different failure in which according to the design, the specimen have been classified. But let's look now to the results in. Okay, no, it's this. Okay, so this is a selection. This is a selection of the test results, monotonic test and pulsating quasi-static test only. In this case, because for sure we cannot apply, let's say, displacement conducting test in compression, let's say, action. What is important to see is also in this case 460 steel has a very good behavior, and I would say also 690 is acceptable. So look, the previous observation and conclusion for tests on material only are also confirmed in this case. To conclude here, first, no problem with welding different steel grades components. Even we are speaking about 235 and 690. The T-stabs realized with high-strength steel show comparable strength with those realized of mild carbon steel. And this is important, thinner high-strength steel end plates of the specimen at similar strength have shown a larger ductility due to the failure in modes 1 or 2 than the thicker mild carbon steel end plates, despite the larger elongation at rupture. It proves a better behavior in low cycle low cycle fatigue. Next, let's say part of the presentation focus on the performance of dual steel frames. I already told to you, but we can repeat. We have dissipative members and dissipative connections, and those members and connections must be able to develop enough ductility. And we have non-dissipative members and connections too, which must remain predominantly elastic, and this have to possess enough hour strength. For sure, the high-strength steel we are using particularly in non-dissipative members and connections, while the ductile components will be on mild carbon steel. This is, let's say, practically the origin of ductile steel structure idea. We have investigated the performance of a set of dual steel building frames, realized following the previous philosophy. We have a set of eccentric braced frames, which are multi-story frames with eight stories, in which the columns are realized by full-strength steel, 460, right? And we have another set of multi-story frames, 16 stories, which combine moment resisting frames with centrically braced frames, conventional centrically braced frames. Again, in this case, we are using high strength steel, but in this case, in those parts which have to remain elastic, which are partially the columns and partially the beams. And we have also the same solutions, but in this case, not conventional centrically braced frame, but buckling restraining braces have been applied. And again, you can see in the bold line the seismic resistant ductile components, and in the thin lines the elastic predominantly remaining members. If we go now to look to the results, I will tell you that the analysis have been, let's say, dynamic analysis. So, and we have applied a moderate work quick with peak ground acceleration equally with 0.24 g, and we have considering three different, let's say, criteria for serviceability limit state, for ultimate limit state, and for collapse prevention limit. And also we have used some acceptance criteria, which means the minimum plastic deformation capacity which must be supplied by the ductile members, and the ductile members are the link deformation in eccentrically braced frames, the braces in compression, and the braces in tension in case of centrically braced frames, and the beam in bending in all the cases. As you could see, both series of frames have been, let's say, dual frame steels, which means a combination between moment resisting and braced frames. So the results, if you are looking to the results for all this, what we can observe is very small deformation, plastic deformation in the non-dissipative design members, I mean columns mostly, for ultimate limit state, which is practically the criteria for safety in usual seismic design. Of course, it is even smaller for serviceability limit. Even for collapse prevention limit states, the values are higher. They still are remaining at the level of be possible to be in most cases repairable after the earthquake. So going further, I have already told to you something about dual structure systems, which combine a moment resisting with braced system. What you have to know, and it is important, in order to consider such, let's say, dual frame system, we must have the participation of both subsystems, moment resisting and braced system. In principle, we are speaking here about the resistance against earthquake. It means against horizontal action. It's for sure the braced frames are the ones which are to expect to resist against horizontal action. But to consider we have let's say a joint action from the both systems, we need to have also a participation of the moment resisting frames, and this could be, has to be at least at the level of 25% from, let's say, the lateral resistance demand. It's good to keep in mind this, because this is something which is important also for recentering system, which is practically at the end the main subject we are targeting in this presentation. We have here three different, let's say, structural solutions of moment frames combined with braced frames in order to obtain, let's say, dual structures. And with such dual structures, we will speak after about the capacity of recentering after the earthquake was passed. We have eccentrically braced frames, which are combined in moment resisting frames. But in this case, the link is not fixed. It is a detachable link, because this is the main ductile component which practically will concentrate the dissipation of seismic energy in the entire structure. The second one is moment resisting frames combined with centrically braced frame, and the braced frames, the bracing system here is realized with restrained brace members. They are also detachable. And the third one is the combination of moment resisting frames with seismic steel ductile walls, which practically have the same function as centrically braces are in a dual frame, and in this case the detachable steel will be the shear wall. What is the let's say the principle of such a dual structure? Assuming a very simple system with two springs, one flexible and one rigid, and you can have here the behavior of rigid system, and you can have here the flexible system, we have to look this as being the braced system, which is rigid, and the flexible one, which is moment frame, but anyway, with the capacity of 25% in taking apart from lateral loading induced by the earthquake. So the rigid one starts to develop plastic deformation. If there are braces, it will be in the braces, while the flexible one remain elastically at level, accepted level of the plastic deformation in the rigid subsystem. This is, let's say, the compound behavior of the dual system. When the earthquake passed, we will have a tentative of the structure to remain to recover the initial position. But for sure, due to the deformation, the plastic deformation of the rigid, only a small part will be possible to be recovered, and this will be the remaining residual deformation. Going now further, we take the same scheme you can see here. At the end, practically, the total plastic deformation, which is the one developed in the rigid component, would include the sum of, let's say, elastic deformation and the plastic deformation of this system. And if you calculate the ratio between this total deformation reported to the elastic limit, we'll obtain the so-called useful ductility of the rigid subsystem. What does mean useful? Does mean we could go even further, because the system, the rigid one, is capable even to develop some more plastic deformation, but we'll stop here because we are interested to keep the elasticity of the moment frame, which is the flexible one. Why? Because this must remain in elastic stage in order to be able to contribute to recovering of initial position, if we will be able to remove the deformed members, the ductile ones, in the rigid component. Let's go. So, in principle, there are two factors to manage the problem. First, we have to calibrate properly the ratio between the yield strength of the flexible and the rigid subsystems by proper design of the structure, and again to calibrate properly the ratio between stiffness of the rigid system and the one of flexible system. So let's go further, and I am going to show to you a validation of such a system, of test validation of such a system for a dual steel frame realized by moment resisting combination with eccentrically braced frame combination. Oops. So what is so this is the frame, and this is the link, a short link, a detachable link because it's bolted, and in principle we have in columns 460 and in the rest of the members 355. More detailing. I have to see. So I don't know what is happening. In the links, practically you have even lower grade, 235. This is the whole structure. For testing, we have used the full-scale simplified model extracted from the whole structure. The tests have been done in the Joint Research Center near Milano of European Union. You can see here the test specimens. We have applied the scheme about we have already spoken. We followed to have at least 25 contribution from the moment frame. This is the situation which I have already discussed with you when no, let's say, recentric capacity was available. And this is the case when we have a recentric capacity due to the fact we can remove the links. So this is like it was before, the rigid, the flexible, the component. We will have, let's say, the unload after the end of the earthquake, and we remain here with the residual stress which is in the link. If we detach now the link, we will get the initial position and the frame practically recover, not 100%, but in a big extent, the initial position. This is, let's say, the recentric behavior when you can apply a detachable member which can act like a fuse. A problem which is important, as you can guess, is the link. The link must be really short in order to develop particularly mostly shear strength, because in case if they are bending, it will be difficult to be, let's say, removed. We have to take into account in designing the link of the overstrength, potential overstrength of steel, and also the strain hardening effect due to the reversal action. In principle, we must have a pre-qualification of the links in order to confirm the capacity of plastic deformation which can be developed by such detachable link. Of course, if you have let's say, a previous test, we can simulate numerically the behavior of the link using validated numerical models. Again, so how we can get the recentric capability? Recentric capability, we speak about recentric only after, let's say, detach of the links. So it's very simple, it's very logical. As I told you, we have practically to ensure that the maximum plastic deformation of the link remains lower than the maximum elastic deformation of the moment resisting frame components. This is something very easy to calculate. A short movie, but I'm sorry, because with this I cannot show to you. So you have to believe me by my word, because all the system is working. Related to the link replacement, also here is not working. So one of the problem is, what is the order of dismantling the links? And sometime, if you have some larger deformation in the link, you must help let's say, remove of the link by using some hydraulic jacks in order to extend a little the space and to extract the link after, let's say, untightening the connection. Again, also here it was a movie, but I have the unpleasure to observe that this is not possible with sorry, look here, look, okay, this is, in this case it was okay. Sometime some dumping, I don't know why. Okay, some damping braces have to be applied in order to secure the bolt tightening operation. That was what you have seen. Let's go further because it's late. Practically, this is the flow chart of main steps in designing such a structure. Is not practically much different to the conventional solution. We have, let's say, this problem to ensure that we will have the moment frame with a capacity of 25% at least in resisting horizontal loading, and we have to keep this in elastic domain in order to have the possibility to recover the initial position after detachable of the link. And we must pre-qualify the link capacity of deformation. And at the end, of course, we need to check the recentering capability, but this is also something which is not difficult to do. So very quickly, it was a full-scale test, but anyway, a laboratory, let's say, structure. We have here two structures, real structures designed according to the code, both using, let's say, detachable links with different systems. You see the structures, and you see here the parameters of those structures, and you have here the members, dimensions, and steel grades. In blue, you have the high strength steel, which in this case is 690. Let's say in gray is 355, which are the ductile component. So, of course, the 690 steel grade was particularly used in order to get enough capacity for recentering. If you look to the results after, let's say, time history dynamic analysis, you can observe what we have already observed: small, really small, let's say, deformation for, let's say, severe, significant damage, which is corresponding to ultimate limit, and of course larger in this case for collapse prevention. Very good Q factor, global ductility of the structures have been obtained in both these two cases. Now we are at the end. We can see practically that the modern high-strength steels, I mean 460 and 690, prove the capability of develop a usable ductility and, of course, resistance necessary, let's say, in a structure which is prone to low cycle fatigue. 460 could offer enough ductility to supply the plastic rotation capacity imposed by the code for beam to column joints in dissipative zones of moment resisting frames. Also, 460 providing the rotation capacity of plastic hinges, which can be ensured in order to, let's say, fulfill the moderate ductility demand in the code, which is 25 milliradians, and apply in these conditions in very good, let's say, safety environment for, let's say, moderate earthquake, 0.20 up to 0.30, let's say, G. When applied non-dissipative members in dual frame systems, high strength steel reduce the ductility demand of dissipative components. This is another very important, let's say, conclusion, which means lower damages in a better control through proper design, let's say, of the structure. This particular, let's say, property is really important for the structure system which are equipped with dissipative fuses of the type I have presented to you. There are here several articles published in, let's say, leading journals related to the topic. I advise you to consult if you want to know more about this problem. Let's say one of them was practically published in steel construction last year, and it was practically devoted to support this lecture. Another European project, let's say, entitled Innovative Anti-Seismic Device and Systems, INOSAIS, let's say, is the abbreviation, studied different solutions in order to protect seismically the structures. Among them are some which are practically applying this fuse concept in seismic protection. And among them is DuaRAM, the replaceable bolted link that I just presented to you. And there is another one which practically show the situation when ductile, let's say, steel walls are applied as also as detachable members. And I think that's all. Thank you.